All right, good morning / afternoon, and welcome to lab number 5, linear actuator control. The biggest difference between this lab and the previous labs is on this one we're using the Elvis board and LabVIEW to develop something to control the linear actuator instead of having an experiment that we're then getting data from and recording and analyzing the data. So in this lab, the main focus is to develop a semi-autonomous control system to position the actuator at a desired position. So you have your circuit set up here. They're very good pictures. I've simplified it a little bit just to make it easier for me. But the pictures at the end of this video / on Blackboard will be very descriptive and show you exactly how to wire everything. So you have your linear actuator here, which can extend from 0 to 50 millimeters. You have your H-bridge here, which is basically the motor control chip. It's very important that you have the H-bridge wired to the appropriate pins, because if you wire it to the wrong pins, the H-bridge will get very hot, could burn yourself, could fry the chip. So be very careful with this. If you have any questions, look on the handout or ask one of us TAs. So basically, I've made the control system myself. You're going to do this yourself. You're going to play with LabVIEW. You'll try out different things. You can try just a linear response where it's just a constant voltage being applied, positive or negative, to extend or retract the actuator. Or you can try a proportional system, a PID system, whatever you want. It's all fair game. You can try to optimize it as best you can. So basically in LabVIEW, I've created a very generic linear response system. If you look at the response of the actuator, I've created this slide. So there's a slide control bar. Right now I'm at 5 volts. So the resistor inside here that measures the distance is getting the entire 5 volts. None of it's going through the resistor. So we're reading a 5 volts across the slide here. So if I go to 0, the actuator will extend so that the resistor absorbs all the voltage, and 0 volts is then outputted to my DAC assistant. So this is just a very poor linear control system. You would never want anything like this. It's very slow. It takes a long time to reach its position. But it does not overshoot. It's a very overdamped system. So you can experiment to try and get an underdamped system, a critically damped system, whatever you're looking for. So a couple things about the VI. We have 2 DAC assistants as opposed to 1. If you notice on the left, there's a DAC assistant that outputs data into the VI, and on the right is a DAC assistant that exports data back to the Elvis board. So the way this works is here we're measuring the resistance or the voltage coming through the resistor in the actuator. We're then comparing it to this slide controller, and then over here we're outputting a true or false signal into the digital output channel of the Elvis board, which then tells the H-bridge whether to extend or retract the actuator. So that's basically the entire purpose of this lab. Just remember, you're trying to optimize the system as best you can. So I have done a very basic VI, as I've said. Try your best to optimize the system utilizing the digital output signals, the analog signals, and I think that's it. If you have any questions, ask the TAs during lab, and good luck.